example, go to some stationary state in a small scale helicity, okay, rapidly, then that suppresses the dynamo because this E dot B, E bar dot B bar becomes just eta J dot B. And that can quench the dynamo. And this one we said goes to 0 as eta goes to 0 many times. So just because of helicity conservation, you could have some kind of catastrophic quenching of the dynamo. So this is one problem that we have been dealing with. Okay. So already the message is clear. You have to somehow get rid of the small scale helicity. That nice simulation which I showed, where you got very ordered fields, that ordered fields arose on what is called the resistive time scale. That time scale was the time scale required to kill that small scale helicity by just resistance. It takes a long time, but in the simulation it can take a short time. So you only get large scale ordered field which avoids the resistive quenching, avoids this kind of quenching, provided you can get rid of the small scale helicity. One way in which simulation did it is by dissipating it. But in a real astrophysical system like where the Reynolds number is very large, you cannot dissipate it. So you have to find ways of throwing it out. In the sun it may be occurring by the CMEs that you see. Helicity may be transported and being ejected. People do not necessarily see the problem in their simulations nor in the mean field models. In the simulation, the Reynolds numbers are too small, in the direct simulation, for at least the sun. In the mean field models, because they don't keep track of the small scale field, what it does. So you need what are called helicity fluxes. Now, flux of helicity is a strange quantity because helicity itself is a topological quantity to do with links and all. What do you mean by a flux of that quantity? Okay. So that also takes time to develop. Okay. So basically I will not get into it too much. I'll just say I'll be running out of time. Okay. So the one kind of definition that we came up with for the small scale helicity density and its flux, at least for a random field you can define this quantity because you sit somewhere, ask what are all the links that I have around me which are correlated to the field here. Since the correlation scale is finite and since the system is bigger than the correlation scale, you will not get correlated links beyond a certain scale around you. You can count that number of links, divide by the volume that you have, and that gives you a density of correlated links. You can make this definition extremely precise by going back to Gauss's linking formula and defining the whole thing, which I will not do here. Then you can write down a helicity conservation equation, and it involves the generation term which I told you, the dissipation term which I showed. It also involves the divergence of a flux. The simplest such flux is just throwing out things. When you just throw out the field, you throw out helicity also. Now, do you have such things in our galaxy? You have, because you have all these supernova remnants. You have the supernova remnants heating up the gas. They produce outflows, and these outflows throw out things. But you have to be a bit careful because when you throw out the field, you may throw out whatever you need also. So the standard thing is you should not throw out the baby with the bath water, right? So you have to be a bit careful when you are doing this. Oh, I wanted to mention this, not much time, but this is a simulation by Pallavi where she started with a helical field and let it decay. And actually it decays very slowly, firstly. Secondly, it generates, the way to understand this is generates this small scale helicity which keeps maintaining it. So I will not get into it much. So what you can do, a simple poor man's slightly improved version of mean field dynamo, if you want to apply it to the galaxy, is to solve the mean field equations, but add the effect of this Lorentz force due to small scale helicity, which I have not gone into it, but it comes as a current helicity term, which was discovered long time back in the turbulence, MHD turbulence literature by Annick Bouquet as a correction to the alpha effect, with helicity conservation equation with some flux. Okay? So you have to then, if you solve both these two equations, This we have called kind of dynamical quenching model for mean field theory. So this is what happens if you have no helicity flux, the galactic field rises because kinematics says helicity has not built up, and then decays rapidly because the helicity has built up to quench the alpha, quench the dynamo. But if you can throw out some flux, then it kind of manages to settle into some good values comparable to whatever you want from the theory. If you have too much flux, then it decays because you're throwing the mean field out with the helicity. Okay? If you have too much of advective flux. You can apply it to our galaxy. If you had no helicity flux at all, you will still grow the mean magnetic field, but it will die. So you will see a ring of field where the growth is faster. This is the radius, again the strength of the field. This is all work done by Luke Chamandi, who is now in South Africa. And because of the quenching, the field dies here, but it is growing slower somewhere else and then it dies. Growing somewhere else and then it dies. So a ring of field will move out in radius if you did not have any flux of helicity, because kinematically you are still able to grow the field by the alpha effect and the shear. Then because of this quenching it dies, but it doesn't die at the same time at all radius because the growth rate is different at different radius, and so you can produce a ring of field moving out. But with the helicity flux you can connect all these fields and the whole field over the whole disk of the galaxy can grow, because now it all saturates to some more reasonable level everywhere in radius. In fact, an interesting question is, if you ask the galactic field has to be coherent over 10 kiloparsec scales, and there is turbulent diffusion which is establishing this coherence, what is the time scale required for it to connect the inner part of the galaxy to the outer part of the galaxy? It will be bigger than the age of the universe. So you will always wonder, how did I have fields come to the edge of the galaxy? Okay? But what happens actually is that the field grows everywhere locally, and then locally it gets smoothed, and you get one thing growing globally. Then you don't need to connect from one page. I also remarked upon that NGC 6946, which had these spiral arms which were uncorrelated with the optical arms. So you can ask, how do you explain such a thing? So Luke Chamandi's thesis was on this, but finally we had an interesting model where this black line shows the optical position of the optical spiral. The colored stuff is where the magnetic field is strong. We had a helicity flux, which you would imagine to be strongest where the spiral arms are, because that's where the star formation is the maximum. That's where the outflows will be maximum. But we had less helicity flux in the inter-arm regions. But it turned out that the helicity flux in the arm region was too large, and it suppressed the field there compared to the inter-arm region, where it allowed the field to grow, and it naturally produced this offset between the optical spiral and the magnetic spiral, with the extra proviso that this, if you know spiral structure theory, people think that it may be one rigidly rotating spiral, and we cannot have that in this theory. So we may be able to say something about spiral structure theory from magnetic fields. Let me take the last 5 minutes to tell you about the other problem. The other problem is, if you have very rapidly growing fluctuations, what happens to the mean field dynamo? This cannot be solved analytically. So first we wanted to see, and here probably I am more the driver than Axel, because these are some things in which I get interested in and I want to know what the answer is. Can you see evidence for the large scale field in the presence of strongly growing fluctuations? That was the question that we had. So Axel ran these simulations where you force the flow at a large enough wave number so that you can see larger scales, small enough wave number so that you can see larger scales, but such that you can also resolve small scales. So that was chosen to be the thing. we actually did this, and the forcing is helical. Now, when you have helical forcing and you think in terms of helicity conservation, a natural way to split the two fields, large scale and small scale field, is to split it in polarization. That is, one is positively helically polarized, the other is negatively helically polarized. And from the theory of mean field dynamo, you can predict that the large scale field will have negative polarization if the alpha effect is positive, or the other way around. Which one? One of them. I always get confused about positive and negative. It's okay. I get confused about subtraction and division, and positive and negative. Okay, so you can make progress even if you are confused, of course. So, so is there an evidence for that? So what we did was to do this simulation and separate in this polarization. Now the spectrum is still peaked. This is a spectrum of one such simulation. Now PM is 0.1, and so it will be probably more relevant to kind of solar context than galaxy context. The reason we try to choose this is that there was some evidence that small PM fluctuation dynamo is inefficient, as Alex was mentioning in his first lecture. But it turns out that if you have large enough forcing wave number, this is not true. So we discovered it in this, and it's equally efficient. So when you split it, you see everything is peaked around the small scale or large wave numbers. So most of the power is in small scales, but the negatively polarized component has an excess at small wave numbers or larger scales. Forcing is here, so there's a bit it sticks out like that. So you can see evidence for, even though all the power is in small scales, you can see evidence for this large scale field here, okay, as in this negatively polarized component. Now you can even show from Kazantsev theory that with helicity, that even in the presence of helicity, in the kinematic regime, the power is concentrated on resistive scales. You can show that from Kazantsev theory, and that's what we have done there. Even though there is a large scale and small scale I'm talking about, it turns out that if you look at the growth rate as a function of k, all wave numbers grow together more or less. There's only one dynamo. There's only one eigenfunction which is growing in the kinematic stage. There's a periodic box, you're doing helical forcing. There's only one dynamo. There's no large scale dynamo, there's no small scale dynamo. There's one dynamo which is kind of growing rapidly at the rate at which the small scale dynamo would grow, dominated by the small scale field. But there's a tail, which is the large scale field, which can be thought of as the slave to the small scale field due to the fact that there is this tunneling possibility. Okay. The sad news at that time was that if you increase the Reynolds number and you define this large scale field, for example, by some kind of averaging, in this case the horizontal averaging, it decreased with Reynolds number. Larger the magnetic Reynolds number, the smaller was this mean field, large scale field. So, I mean, imagine you're going from 160 to 10 to the 19, you'll have no mean field. But this is kinematic. We are just trying to see in the kinematic stage what happens. So then the question naturally occurs, what happens in the nonlinear stage? And for that, again, more recently, Pallavi has run a very high resolution simulation, 1024 cube. How long did it take? Few months?
This was
1 month. Okay. Took about a month on the IUCA cluster. Again, forcing is at k equal to 4. The kinematic stage is more or less like whatever Axel saw in his simulation. The power is peaked at the resistive scale. Okay. This is the kinematic stage. The large scale field kind of sticks out in the polarized component. Okay. Everything is still peaked at the resistive scale. The growth rate at the kinematic stage is independent of wave number. Everything goes as one eigenfunction. But as the field grows, you can see that it's ordering itself in the sense that the peak is no longer here, but it's shifting, and right at the end of the simulation, there are two peaks. One is at the forcing scale, one is at the box scale.
Which is p equal to 0?
T equal to, this is 100 already. T equal to 0 is random noise. You start with random noise basically.
That's what I wanted to say. P is small. This P is small, no?
Yeah, 0.1.
P is small, the growth is at the small k.
Small scales. I thought you were saying that
Small k, small wave number.
you can see that even though growth may be, but spectrum will peak at the large k. You should check your spectrum.
So that's but you see, now here there is not which time. So here
No, there is no, see, there is, as I have said, if you look at the growth rate, it's just one growth rate. And the kind of, where is that? Here. This is the growth rate calculated at every wave number. And there's just one growth rate in the beginning, in the kinematic state, which is what you expect. You expect an eigenfunction of the whole dynamo to grow in this box when no Lorentz forces are involved. You start with whatever initial condition you want. It will adjust itself to one eigenfunction. That eigenfunction will grow. Now, what happens at nonlinear stage is what is important. What is interesting also. At nonlinear stage, it turns out that the field orders itself on larger and larger scales. Finally, you get two peaks, one at the forcing and one at the box. Now, I will come to both these peaks. It's also interesting to see this plot where what Pallavi has done is to plot at each wave number the power spectrum. So this is at 500, as you can see 200, 50, 4 and 1. 1 is the box scale basically. So you can see that they all more or less start off going the same way. The slope of these different curves are not very different, at least in the early stages. But as time progresses, each one of these saturates, the higher wave number saturates first, then lower, then lower, then lower. There is no real indication, and we had a lot of arguments and finally she won, that there are two dynamos, that there's a small scale dynamo and there's a large scale dynamo, which is what I wanted to see. But what you basically see is one dynamo where larger case saturate first and smaller case keep growing. Okay. Of course, I must put one caveat. I mentioned the helicity problem. Here the helicity problem is being solved purely by resistive dissipation. You have to solve both problems. You have to solve the problem of noise, you have to solve the problem of helicity. We are not having any fluxes, nothing. There is a closed periodic box. The only way helicity changes in this system is by resistivity. So final growth of the large scale field comes because of resistive thing. But the initial thing is not because of that. It is everything is growing together. Okay? And if you look at the spectrum at different times, initially the growth rate was uniform, then as you can see in a different way. The large case stopped growing, and at final time everything more or less stops growing very slowly. Or this is the mean field now. There is this catastrophic quenching. Smaller Reynolds number have more mean field than larger Reynolds number in the kinematic stage. These are all still growing. The expectation will be that all of them go to the same point finally, because in these boxes, the final saturated state is when the helicity stops evolving, or the total J dot B becomes 0, or the large scale J dot B and the small scale J dot B compensate each other, or basically the mean field is like some fraction of the turbulent energy density. Okay, so I think I've taken 5 more minutes. Let me stop just putting these questions. Thank you.
We are talking about the shapes and links and the reading and twisting. There's a very interesting surface which is shown here. It's called Mobius strip.
Yes, yes, yes.
If something like that we can take in that, I think we can prove the helicity point very more effectively, because the surface itself is complicated. It's like a strip. You start on the other side and normal goes.
Yeah, I mean, you see, yeah, I mean, there was a recent paper on Mobius strip, but anyway, I think Anwar has done something on decay of this Mobius, something like a Mobius strip thing. It's a paper, but
it could be represented as loops also. I mean, there are multiple representations and equations are there.
right, right. In fact, Axel had a student who was decaying various things, including the IUCA symbol. Because are there other invariants than just the helicity? Helicity is a quadratic invariant. There may be more complicated stuff like this. And like, for example, the IUCA symbol which I showed has zero helicity, but it clearly has a topological non-trivial property. So how would that kind of thing change? And does it change slowly, fast? So these are unanswered questions. Yes, Chris. Chris. Oh, it will be just, in periodic box, it will be just sines and cosines. It will be the eigenfunction of the alpha squared dynamo. That is random. It will choose it randomly. Different realizations will choose it differently. Yeah, you are doing small scale forcing at k equal to 4. So the k equal to 1 field finally, at the final saturated state, will be like the one which I showed you, but that will be randomly chosen. I mean, this one. This one. See here, for example, it has randomly chosen to be varying along this direction. It could well have chosen the other way or any three of those directions, which are all eigenfunctions of the helical alpha squared thing in the box. Again, what are they called? Chandrasekhar-Kendall functions. They are curl B equal to B functions with k equal to 1 as the variation. So they are just sine and cosine. For the two component, the third component will be 0. Two components will be sines and cosine. The third component will be 0. And they will vary along one direction, x, y, or z. And that will be chosen arbitrarily, randomly because of the initial condition, whatever you put. Previous, I have forgotten, but okay.
Sir, while measuring the Faraday rotation,
Right.
what is the reference magnitude? And what is the reference angle? I mean, how do you know the?
Is it big or small?
No, I mean, from where?
Oh,
The zero.
how do you know the reference? Very good question. You have to extrapolate to lambda 0. The thing is, you only measure some angle. You don't know what is the, you measure the angle at some lambda 1, some lambda 2, hopefully at a lambda 3 because you want to draw a straight line and you need 3 points for that straight line. Okay, so you just put whatever angle you measure at these 3 points, and you know that it has to go as lambda squared. So divide, you plot the phi versus lambda square. Okay, and wherever it cuts lambda equal to 0, that was the original polarization.
Based on the relation between phi and lambda.
Yes, so you have to believe that equation, correct. If you don't believe that equation, which can happen because you have so many depolarizing effects which can all do random. One of the depolarizing effect could be just the random fields which will randomly rotate this stuff. Okay, yeah, you are in soup, you can't do anything. You have to, it's a self-consistent thing in the sense that if it does pass through a straight line, then you say, I mean, at least on this scale you have an ordered field which is causing Faraday rotation. If it doesn't pass through a straight line, then you are sunk in this particular way. But you can look at the depolarization, that you had a certain amount of polarization and does it change with wavelength? And one of the effects, if it changes with wavelength, how much it gets depolarized. One of the reason would be because there are magnetic fields which are random, which are randomly rotating this polarization angle. But at different wavelengths, it has stronger or weaker effects.